Hello, my name is Bob Rehder, and I'm from New York University, and I'm presenting the paper Testing a Process Model of Causal Reasoning with Inhibitory Links. My co-author is Zach Davis, currently at Stanford University. The last several decades of research have shown that causal knowledge has a profound effect on virtually all types of human judgments, including how people reason and make decisions, how they categorize, and how they learn and explain the world around them. Moreover, this empirical work has been accompanied by the use of causal graphical models as a theoretical framework of how to represent and reason with causal knowledge. Causal graphical models are a formalism borrowed from artificial intelligence that serves as a normative benchmark against which human causal-based judgments can be evaluated. In fact, causal graphical models have provided a good first-order account of human causal cognition, explaining phenomena such as sensitivity to causal direction, the phenomenon of explaining away, and how people anticipate the effects of their interventions. However, causal graphical models have a limitation, which is that they are a computational account of cognition. They specify what, but not necessarily how, specific computations are carried out. In response, last year Zach and I published a paper in which we proposed a new model called the mutation sampler that specifies the mental processes via which causal inferences are drawn. Notably, the mutation sampler is an example of a rational process model, a model that yields normatively correct answers when infinite cognitive resources are available, but begins to make errors when limitations on those resources are introduced. So today I'm going to describe the mutation sampler. I'm then going to describe how it accounts for existing causal reasoning errors, such as Markov violations. I'm going to derive predictions for a new type of Markov violation, and then I'm going to report an experiment documenting the existence of this new error. The mutation sampler derives predictions by estimating a causal graphical model's joint distribution. It does so via Markov chain Monte Carlo sampling over the graph states. As the number of samples grows large, the estimate converges to the true joint, but because cognitive limitations entail a small number of samples, systematic errors in the representation of the causal system are introduced. Here's an example of a simple causal graph in which variable C is a cause of both effect variable A and effect variable B. And here is the state space of this graph, assuming that variables are binary. In each of the 8 states, filled-in circles mean that a variable is present, and open circles mean that it's absent. The mutation sampler sequentially samples these states by using the Metropolis-Hastings rule to choose whether to move from the current state, here called Q, to a new proposed state Q prime. This function yields the probability of whether in fact the transition occur. That probability is the ratio of the likelihood the system is in the proposed state and the likelihood that it's in the current state. Here's an example of a chain of samples generated by the Metropolis-Hastings rule. Suppose that sampling begins at the 111 state, the state in which all variables are present, and suppose that state 110 is proposed as the new state. We compute the ratio of the likelihoods of the two states, which give us the probability of moving to the proposed state. In this case, we accept the proposed state, and so it becomes the new current state. We now repeat this process, proposing a new state and computing the probability of accepting it. In this case, we don't, and so the current state is retained as the next state. And this process continues until a sampling chain of the desired length is acquired. After sampling is complete, we simply count up the number of visits to each state and then normalize, thus yielding an estimate of the causal graph's joint distribution. That is, the result of sampling is to assign a probability to every state of the causal system, and that joint distribution can be used to derive other important quantities, such as conditional probabilities. There's one other important assumption made by the mutation sampler, which is that sampling always begins at one of the two prototype states. We define prototype states as those in which the variables are either all present or all absent. Here once again is the state space of our example causal graph, and here are the two prototypes. On the upper right is the prototype in which all 3 variables are present, and on the bottom left is the one in which they're all absent. We believe that these are reasonable states at which to start sampling because they are easily seen as being qualitatively consistent with the graph's causal relations, at least when the relations are generative. That is, ignoring quantitative details of the graph, such as the strength of the causal relations, or even the direction of the causal links, a reasoner can assume that the prototypes are high probability states and thus good places to start sampling. In fact, in our paper we show that initiating sampling of the prototypes often results in faster convergence to the true joint distribution. However, another consequence of this assumption is that the mutation sampler yields an estimate of the graph's joint distribution that is systematically biased. In the graph, the blue line shows the normative joint distribution for our example graph under some parameterization. In contrast, this joint shows the one estimated by the mutation sampler when the number of samples taken is 4, and this is the one for 8 samples, and then this is the one for 32 samples. As you can see, as the number of samples increases, the joint distribution estimated by the mutation sampler begins to closely approximate the normative one, the blue line. But also as important is the fact that because sampling started at the prototype states, they are systematically overrepresented in the estimated joint distributions. And the consequence of the prototypes being overrepresented is easy to describe. Because in both prototypes the two effects are either both present or both absent, their impact will be to introduce a small positive correlation between the effects into the sampling chain. And that's important because any inference based on the biased joint will itself be biased. For example, conditional probability judgments will reflect the positive correlation between the effects introduced by the prototypes. And to illustrate this, it will be convenient to look at some conditional probability queries that have been used to demonstrate something called the Markov condition. So what is the Markov condition? Well, according to the Markov condition, a variable is independent of its non-descendants conditioned on its parents. In our example graph, effect A and effect B are non-descendants and thus are defined to be independent conditioned on their parent C. The intuition is that C is the direct cause of effect A, so once you know about the state of C, effect B provides no additional information about effect A. We say that effect A is screened off from effect B by C. Let me show you some example conditional probability queries that illustrate the Markov condition. Suppose you are asked to estimate the probability of effect A given that the cause is known to be absent, as shown here by C equal to 0, and that no information about effect B is provided. Well, whatever answer you come up with for this query, it shouldn't change if you then also learn that effect B is present, as shown here where effect B is set equal to 1. Because the Markov condition stipulates that effect A and effect B are independent conditioned on C, knowing about the state of effect B should have no influence on your estimate of effect A. And of course, the answer also shouldn't change if you learn instead that effect B is absent. That is, you should give exactly the same answer to all three of these queries. The same is true if instead you are asked to estimate the probability of effect A given the presence of C, C equal to 1. You should give the same answer if you also learn that effect B is present, or if you learn that effect B is absent. These three queries should also have the same answer. So, how does a biased joint affect conditional probability judgments? Well, for a non-biased joint, shown here in blue, the conditional probability queries I just showed you have to have the same answer, as represented by the horizontal blue lines. But the biased joints estimated by the mutation sampler will necessarily yield biased conditional probability judgments. They will be biased because the prototypes, which are overrepresented in the joint distribution, embody a positive correlation between the effects. As a result, the independence relation stipulated by the Markov condition will no longer hold. In particular, the presence of effect B will make effect A more likely, and the absence of effect B will make effect A less likely. In fact, human causal reasoners systematically violate the Markov condition in just this way. For example, here's some data from an experiment by myself and Michael Waldman from a few years ago. The gray bars are the ratings the subjects produced in response to the key conditional probability queries, and in fact, these subjects violated the Markov condition. This is made obvious by the best fit of the normative model to these data, shown here by the horizontal blue lines. In contrast, the mutation sampler is able to reproduce the pattern of Markov violations exhibited by the human subjects. That is, not only does the mutation sampler violate the Markov condition, so do human reasoners and in the predicted direction. I've described just one study, but in fact Zach Davis and I found that the mutation sampler provided a better fit to the judgments of more than 2,000 subjects from 45 experimental conditions using a variety of causal-based tasks, not only conditional probability judgments, but also categorization judgments, predictions about interventions, and so forth. Today we report the results from 4 additional experimental conditions testing the mutation sampler. In particular, we derive novel predictions for inferences involving inhibitory causal relations, that is, relations that make an effect less likely when the cause is present rather than more likely. Our first condition is just a replication of the one that I've been showing you, in which subjects reason on the basis of a common cause graph with two generative relations. As we've seen, the prototypes are the states where variables are all present or all absent, and those states embody a positive correlation between the effects. Here are the predictions, which we've already seen. Those of the normative model in the horizontal blue lines honor the Markov condition. In contrast, the predictions of the mutation sampler, the red lines with positive slopes, reflect the positive correlation between the effects. In contrast, we get new predictions in the second condition, in which the causal relation between C and effect B is described as inhibitory rather than generative. As a result, in the prototypes, whereas effect A continues to have the same value as C, effect B should have the opposite value. Importantly, this means that there's now a negative correlation between the two effects, and this means that although the mutation sampler still predicts Markov violations, those violations should now be in the opposite direction, as shown here by the red lines with negative slopes. That is, the presence of effect B should make effect A less likely, and the absence of effect B should make it more likely. In the third condition, it is now the causal relationship between C and effect A that's inhibitory. In the prototypes, it's now C and effect A just have opposite values. This again yields a negative correlation between the two effects, and so once again we get Markov violations in the negative rather than positive direction. Finally, in this last condition, both causal relations are inhibitory. As a result, both effects have values opposite of C, and the result is that there's now once again a positive correlation between effect A and B, and as a result the mutation sampler once again predicts Markov violations in the positive direction, as shown by the red lines with positive slopes. To summarize, we predict Markov violations in all conditions, but predict those violations will vary depending on whether the causal relations are generative or inhibitory. When they're all generative and all inhibitory, as in the far left and the far right, we expect positive Markov violations, but when there's a mix of generative and inhibitory relations, as in the two middle conditions, we expect negative Markov violations. Note that, to our knowledge, the question of how Markov violations vary with whether the causal relations are generative or inhibitory has not been previously tested. So, 72 subjects were taught causal knowledge that formed a common cause graph. Whether the causal relations were generative or inhibitory was manipulated as a between-subject variable. They were then asked the key conditional probability queries. Let me start with the conditions in which the causal relations were all generative or inhibitory. Remember that in these conditions we predicted Markov violations in the positive direction, and in fact that's what we find. Here the gray bars are the ratings produced by the subjects, the horizontal blue lines are the best fit of the normative model, and the red lines are the best fit of the mutation sampler. As you can see, the red lines with the positive slopes indicate that the mutation sampler once again reproduced subjects' Markov violations. Now let's look at the conditions consisting of a mix of generative and inhibitory relations. Remember that in these conditions we predicted Markov violations in a negative direction, and that's what we find. As you can see, the red lines with the negative slopes indicate the mutation sampler once again reproduced subjects' Markov violations. In fact, in all conditions, we found that the value of effect B had a statistically significant effect in the direction predicted by the mutation sampler. As a result, the mutation sampler achieved a superior fit to these data as compared to the normative model, even correcting for its extra parameter. So, to summarize, empirically we've documented new types of causal reasoning errors. First, for the first time, we found that Markov violations occur in a causal graph with nothing but inhibitory relations. Those violations were in the typical positive direction. Second, for causal graphs contained a mixture of generative and inhibitory links, we found that people still commit Markov violations, but now the sign of those violations has switched from positive to negative. To our knowledge, this is the first demonstration of Markov violations in the negative direction. The important theoretical result, of course, is that each of these effects were predicted beforehand by the mutation sampler. Remember that as a rational process model, the mutation sampler explains why human causal inferences approximate normal ones. This is important because people generally reason causally pretty well. But because cognitive resources are limited, it also explains why humans commit systematic errors, such as Markov violations. In our previous work, we used the mutation sampler to explain why positive Markov violations occur. Today, we've not only shown that Markov violations sometimes occur in the negative direction, they do so in just those conditions predicted by the mutation sampler. And thank you for your attention.